We've already seen the nucleophilic substitution reaction where we took a hydroxide ion and showed how it could replace a halogen atom that was found in an alkyl halide or halogenoalkane. Right? We'll examine the mechanism in a little bit more detail for those of you writing the higher level exam. This occurs, again, when a halogen is replaced by a stronger nucleophile, such as hydroxide. Okay, other examples would be water, ammonia, or the cyanide ion. Cyanide ion will also, so that's Cn negative. That may come up because that's a common way for us to show you how to extend carbon chain length. Right? But again, hydroxide will be the most common that you'll work with. I'm going to draw a representative alkyl halide here, and I'm going to use the same molecule, or essentially the same molecule, for both SN2 and SN1 mechanisms. All I'm going to do is move the position of the halogen. So I'm going to use 1-bromo 2-methylpropane as my representative molecule, and the purpose of the positioning here is I want the bromine to be found on a primary carbon, as shown right here. Right. This is important because the SN2 mechanism is favored when your alkyl halide, or when your halogen, occurs at a primary carbon over either a secondary or tertiary. Okay, and this is due to the idea that the reaction occurs all in one step. So this bimolecular notion means both particles that are involved in the reaction come together in a single step. This is not a two-step process, right? So essentially, the more freedom that is found around the carbon atom, right? So a carbon that's bonded to 2 hydrogens and only 1 other carbon has a lot more open space around it for the attacking nucleophile, in this case hydroxide, to come in. All right. Also, SN2 is preferred here because the SN1 mechanism, which we'll see occurs faster, requires a charged intermediate, and a primary carbon cannot stabilize a charged intermediate well. Right. So we may, as you heard me just mention, this reaction occurs all in one step. This is why we call it bimolecular. We could express the rate law for this reaction as shown here, where we would need both the alkyl halide and hydroxide ion concentrations there. So what we would show happen, mechanistically speaking, we would show a pair of electrons attack the carbon atom from the hydroxide, and then the pair of electrons found in the carbon-bromine bond are then deposited completely onto the bromine atom. Okay, this occurs best in a polar aprotic solvent. Aprotic means it cannot release a proton. All right, so the best example of this, and most common really, is acetone, also known as propan-2-one by its more correct name. Right, the resulting molecule would be 2-methylpropan-1-ol. Okay, as shown here, okay, with the hydroxyl taking the place of the bromine on the primary carbon.